Okay. Well, we're going to try that. If I could have your attention. Here's what we're up to today. Yes, I do have a derivation. I think that cat has been let out of the bag. But also, we have several things that we're going to look at today. If you have started the homework problems, you'll be able to understand them much better with what we do today. So far we've seen delta G and how it's equal to delta H minus T delta S. This is a really big deal. As I mentioned, I can't remember what day, either Thursday or Friday. If delta G is negative, the reaction, the way it's written, is spontaneous. It's going to happen. That's the most important thing in the whole chapter 17. Now, the delta H can be positive or negative, and delta S can be positive or negative. How do the signs on those contribute to what the sign on delta G is going to be? And I have mentioned, this is the last slide that we had on Friday, and I said, well, look at this. There will for sure be questions about this in your homework. There for sure will be a test question about this, and I would guess that on the AP exam, you'll have a question at least about this. So this is
negative delta H and positive delta S. It's always spontaneous.
Yes. Oh, I have a little eraser there. Maybe I can get rid of that. Where's my eraser? Okay. So anyway, a spontaneous reaction has a negative delta G. Still got my eraser on. The first scenario is when delta H is negative and delta S is positive. Now it turns out, I've mentioned this a couple of times already, that nature tends to get rid of its energy. If nature had a preference, it would prefer to release stored energy. So that delta H is the heat energy that I'm talking about. When the delta H is negative, that contributes to a negative delta G. That helps delta G to be negative. When delta S is positive, look at the math on this. Does a positive delta S help delta G to be negative? Does a positive delta S help delta G to be negative? Yeah, because we're subtracting. Now, what about the temperature? We use the temperature in Kelvin, and it has no negative values. So this number is always positive, and therefore a positive delta S means that we're subtracting a positive number. The number is becoming more negative. You with me? So no matter what the temperature is, if your delta H is negative and your delta S is positive, the delta G is going to be negative and the reaction will be spontaneous. At a low temperature, a high temperature, any temperature you want to use the reaction at, it's going to make a negative, it'll be spontaneous. Yes?
So like, with like the equation, is it saying like the product, delta H of the products minus delta S of the reactants?
Yeah, when we find delta H, it's the products minus the reactants.
Okay.
Yeah. You're not asking me, Jazz. You're not asking me if this is delta H of the products minus delta S of the reactants, are you? We're not mixing those two and putting them in the same equation. You'd find delta H with products minus reactants from the table. Then you find delta S taking the products minus reactants from the table using the S terms.
Okay, that's okay.
Yeah, you can't put them together. It's not these products minus those reactants. That's not what I'm saying.
So delta H of the products and the reactants.
Yes.
Okay, and that.
Yeah. Avani?
So I tried applying that to like number 35, would it give you the delta, actually the delta S and
Yeah.
T?
And then you're
But-
asked to find delta G, right? Or is it given to you?
No, they just say like, will it be spontaneous?
And they're giving you the delta G value?
No.
Okay, so you have to do this.
Yeah, but can you just tell just by looking at it? Or
Yes, if you know the sign on it.
Yeah.
No, if this is positive and that's negative, then yes, you can just automatically know that delta G is going to be negative because of this. It's spontaneous no matter what the temperature is. However, that's great. So this explanation is going to kind of walk you through how to do that one. Because if you have a case where they're both negative, and the question is it spontaneous or not, you want to know if delta G is going to be negative. Did it give you the temperature in that problem?
Yeah.
Okay, so you'd have to calculate the delta G in that.
It's like,
Because of this, I mean, It depends on what the temperature is going to be. If they're both negative, you have to look at what the temperature is.
So if
and
they ask
calculate.
you, would you still write down spontaneous even though it's only in like certain conditions? Or would it be
At that temperature, if delta G is negative, that's the only way you'll know. You'll have to calculate the delta G.
Temperature is always positive because it's Kelvin, right?
Because it's in the Kelvin scale. Yep. Sir?
I saw this like equation in the solution that says negative delta S surroundings equals as system. Yeah. Does that mean that if you add?
No, it didn't say that. The surroundings does not equal the system.
Yes, it
Wait,
did.
it
The delta S of the surroundings equals negative delta H over T.
Q system equals negative Q surroundings.
That's Q, that's the delta H. That's not delta S.
Oh.
Like you and I were talking about that one, this one. This is the flow of heat. That's Q, that's true for. But entropy is not conserved in a reaction. Entropy is not. The entropy change in the surroundings is not related to the entropy that's changing the system.
So it could be anything.
Yeah. You might have both the system and the surroundings becoming more disordered. Yeah. Or one less and one more.
Wait, I have to say how many problems?
Oh, a bunch. You'll be able to do almost all the rest of them. Yeah. I mean, I'm going to be down to like 3 or 4 slides by the end of the hour today. So we'll know almost everything. Yeah. You might be able to do all the problems.
Will we do the equation with the LM?
Yes.
Is that what we're deriving?
We're doing that today, yeah.
We're deriving that?
No.
Are you, so we're never gonna, are we gonna apply LM to the stuff?
Yeah.
Yes. Yep. You might have to. Yep. I'm walking you through that. That's okay. It's not terrible.
Then we're gonna need a graphing calculator.
Nah.
Yes, but scientific calculators can't do that.
All right. So bear with me on this one. This is for Shannon and others. So if delta H and delta S are both negative, if this term is negative, the negative delta H helps the delta G to be negative. However, the negative delta S does not help the delta G to be negative because we're subtracting a negative number. It's like we're adding. This term is becoming more positive. You see that? So this is not helping delta G to be negative, but the delta H is. So this will only be spontaneous, and delta G can only be negative if this term dominates. We need the delta H to dominate this one. So that's why I say this is spontaneous only when this term has a low temperature, and therefore the delta H is going to kind of win out and make delta G negative. So you need to know that when both terms are negative, negative delta H and negative delta S, the delta G is only negative when the temperature is low. On the contrary, if they're both positive, that means that, I'll get rid of those, this is a positive term, and this is a positive term. The delta H is not helping delta G to be negative, so, however, the delta S is helping the delta G to be negative. So we need this term to dominate. So if we want the delta G to be negative, then the reaction can only be spontaneous if the temperature is high. This term has to dominate. The last case, or possibility, is where delta H and delta S are both unfavorable. The delta H is positive, which means it's got to take in heat, and the delta S is negative, which means it's becoming more ordered. If this is positive, and it's subtracting a negative, it's making it more positive, the delta S term is making it more positive, then delta G will be positive no matter what the temperature is. So when you have a positive negative for the delta H and S, it's going to be non-spontaneous at all temperatures.
Is there like a table for this?
That is, no, there's no
Positive
table
delta
for
H
it.
and negative delta.
Yes, there is. Look at the
Because,
stuff, it's in the book.
Did they give a table that describes this? Okay. Okay.
It was part of the reading quiz.
Oh, yeah.
No, well, the reading quiz was about the entropy only. It wasn't about delta G. But yeah, I wouldn't be surprised, I guess, if the book has a table for this. And this is something that you have to know. Like I say, it's and being able to apply it. Like that was the very last question in the practice test, right? Yeah, the last question, the practice test, gave a graph like this. It gave temperature and delta G. And the delta G was going like that. And at a certain point, it was 0. This is where delta G is 0. So it looked like as the temperature goes up, eventually you get to delta G 0. Down here where delta G is a negative value, this is where the reaction is spontaneous because delta G is negative. This little dashed line, I've got that jumbled together. But that dashed line is 0, 0 delta G. So, yeah, where this is a reaction where at low temperatures, the reaction is not spontaneous because delta G is positive. At high temperatures, the reaction is spontaneous because delta G is negative. It looks like this scenario. Yes? It's only spontaneous when it's a high temperature. So that only can happen when both are positive. That's the way I want you to think about that. Okay. Another thing that we had skipped this on, I'm going back one slide, on Friday. If we look at this chemical equation, it's not really a reaction because it's just a physical change. Solid ice changing to liquid water. It's just the melting of ice. We can measure what the delta H and the delta S are for that change. And I'm giving you 3 different temperatures. 3 different temperatures for this reaction. And the question is what's the delta G and is the reaction spontaneous at these 3 temperatures? Now, let's talk about negative 10 degrees Celsius. From your experience, not from any calculation of delta G, just from what you know from living your life, is this change, solid ice change into liquid water, spontaneous at negative 10 degrees?
No, it would be ice.
It stays as ice. If you have ice, it's not going to melt at negative 10. You just take a chunk of ice at negative 10 degrees and sit it in a room where it's negative 10, and you watch it and think, okay, I'm just going to wait for this to melt spontaneously. You're going to get really, really cold waiting for it. It's not ever going to. Samir, don't be like that.
I know, right? Stop. Oh my God.
So anyway, this is not going to happen. Well, if we calculate the delta G of this, anybody have a calculator up? Do you have one handy?
Human calculator.
All right. So if we were to calculate, we know that delta G equals delta H minus T delta S. What is the delta H is given to us? 6,033 joules per mole. There's our delta H minus the temperature, which is negative 10 degrees. Got to change it to Kelvin. 263 Kelvin.
220.7.
Positive or negative?
Positive.
Okay. Thank you. Positive 221, did you say?
220.7.
Oh, 220. Let's just call it 221. The delta G is positive 221 joules per mole. What do you know about a positive delta G value? It's not spontaneous. What do you know about the opposite direction of the reaction if the delta G is positive? If it's not spontaneous in this direction, what does that mean about that direction? It is spontaneous. Yes, it is, for sure.
What do you mean, what direction?
Yeah, in the way that it's written, from left to right, it's not spontaneous going that way. But as you know, if you put a tub of liquid water into an environment where it's negative 10 degrees Celsius, then it'll freeze spontaneously. You don't have to do anything to it. You don't have to apply a pressure to it. You don't have to do work. You just let it go and it freezes on its own. Now, take a look at the 0 degrees Celsius. What happens with solid ice at 0 degrees Celsius? Well, delta G in this case would be 6,033 minus 273 Kelvin this time because the temperature is now 0 times 22.1. What do you get? Zero. You're going to get something that's very close to 0. It does not come out to exactly 0, but it's like negative 0.3 or something like that. So I'm just going to say that the delta G is 0. And what does that mean? What does that mean if the delta G is zero? If we know if delta G is negative, it's spontaneous in that direction. If delta G is positive, it's spontaneous in that direction. What about zero? It means it doesn't go that way and it doesn't go that way. It's not going to do anything. There's nothing that drives it one way or the other if the delta G equals zero. And so anytime you're dealing with a phase change, listen to this because this is going to be in the problems too. Anytime you have a phase change, at the phase change temperature, delta G is zero. So really the question is, what does ice do? If you take a solid chunk of ice and you put it in a room where it's 0 degrees Celsius and you walk out and you wait for the ice, is it going to melt in that environment where it's 0 degrees Celsius? No, it stays as solid ice because the delta G is zero. There's nothing in nature telling it to go that way. You have to have a negative delta G for that. Now, if you have right next to the ice a pot of liquid water, this would be an amazing experiment. If it was exactly 0 degrees, your chunk of ice wouldn't melt. And if you have a pot of water in there too, it wouldn't freeze. Because the delta G is zero, so it's not going that way spontaneously, and it's not going that way spontaneously. So what is water at 0 degrees? Well, it could be a solid, it could be a liquid.
Yeah, but you have to hold the water in something, and that might get colder.
Right. If you take the temperature of the room, go to the thermostat and go down to -1 degree Celsius, then eventually it'll take a while, but it'll freeze. Yeah. Because the surroundings are...
The liquid would have to be suspended in something like plastic, so wouldn't that get colder than 0?
No, it would stay. It would stay whatever the environment's temperature is. Yeah. Because, as soon as the water is warmer than the environment, the water's going to start giving heat to the environment. That's the first law of thermodynamics. When one thing is colder than another, the warm thing is going to give heat to the cold thing. And so, yeah, the water would freeze if you cooled it just down by 1 degree. But if you leave it at 0 degrees, the water stays liquid. And if you have ice in there, the ice stays solid. It doesn't do anything. It's not going to the right, it's not going to the left. Yes?
So that means like something won't freeze if it's at 0 degrees Celsius.
Correct. If it's right at 0 degrees, it doesn't freeze. Yep, it's got to be lower than that.
Wait, so is that, like how they give you like a boiling point and like a freezing point? Does that mean that it has to be lower than that? Because like if the temperature, because like the freezing point of water is 0 degrees Celsius.
Yeah.
Doesn't it actually have to be lower than that for it to freeze?
No, the environment has to be lower than that so that the water is warmer and the water can give heat to the environment so that it can freeze. It's got to be able to get rid of heat. So if the water is at 0 and the environment is at 0, there's no exchange of energy, and so the water just stays as liquid. Yeah? It's a weird thing. I know. You think, oh, as soon as water gets down to 0, it just freezes. No. Its environment, it's got to be still getting rid of heat, and if it's the same temperature as the environment, then it just stays that temperature and doesn't change. There's got to be a flow of heat out of it. All right, I got 3 boxes here, and each box has 10 particles inside of it, 10 gas particles. You can count them if you want to, Danny. There's 10. Which of those 3 boxes has the most entropy?
The first one.
Why?
Because it's like there's more disorder because they're like tightly compacted.
Samir, try again.
Well, like
Wait, it's like the
What is entropy?
disorder.
It's disorder. Keep talking. It's also
When the
combo.
possible arrangements, right? We talked about entropy being a function of positional probability, right? Which of these 3 boxes do the particles have more possible arrangements in? More possible arrangements, yeah. The positional probability part is a big deal, and we do have to understand entropy like that. Yeah, I mean, the particles can be in more possible places when the container is bigger. So I would contend that the larger container is the more entropy. Now Gibbs gave us the delta G equals negative delta H, not negative, delta H minus T delta S. He also came up with this. This is where we have the dreaded ln term. Yeah. Let me see the hands of the people. There's no shame in this. How many people are currently in Algebra 2? Let me see your hands. And this, like I said, seriously, no shame at all. That's fine. That's good. If you're in Algebra 2 right now, you haven't seen logs or ln yet. if you are in pre-calc or higher, then you have done logs before. And so I am not going to have you, I'm going to show you a derivation of something. It's going to involve logs. You will not be responsible for deriving anything that involves logs. The most you're going to have to do is put a number into the calculator with an ln in front of it and find an answer for it. Yeah?
What about on tests? Like, you can't use calculators.
No, nobody can use a calculator on a test. When you're trying to do the ln of a number, nobody has ln values memorized. I know there's some people that look over to the left side of the room like, you don't memorize ln values, I assume. The only ln value I want you to know is the ln of 1. What is it?
0.
Right. ln of 1 is 0. Everything else I would give you. So if I had a problem that involved an equation like this, I would give you what the natural log of the number was. Like if we had to take ln of 15, I'd say ln of 15 is this number, so you can just plug it in. Okay? Now, okay, now the degree sign here is the standard value. So what I'm saying is the free energy of some gas. Now we have to deal with gases here because of this pressure term. Liquids and solids don't exert pressure like gases do. So this is specific to gases only. What Gibbs said is that the free energy of a gas would be equal to its standard free energy plus RT, R is the thermodynamic constant, 8.31, times the Kelvin temperature, times the natural log of its pressure. Now, as a gas reacts, its pressure changes. And when its pressure changes, that causes this amount of free energy to change. This term right here is the standard free energy. It's a constant. And I should write that on here. Anytime you see a delta G or S or H with a degree sign, we really call that a naught sign. N-A-U-G-H-T. It's like naughty, but without the Y. So without the Y, it's a nice word, right? Naughty is not so good of a word, but this is called G naught. It's like a British term. Those British. They're good. They're good. Help us out.
Whenever you're deriving something, you always have to hate on it.
I know. Like you physically you're unable to.
Wait.
I just have fun with them. I'm not hating them. Although, you know, the British sometimes, I'll tell you the one thing I hate that the British do. And I wish, I would just like to punch every Brit that does this. Because they're wrong. When they say aluminium.
Oh,
I don't like that.
they invented a language. It's not wrong.
No, that doesn't matter. They're doing it wrong. Yeah, they need to change that.
Or when they called color with a U.
Aluminium, they wrote it wrong, and then they actually changed it back to aluminium, and it's just, we just stuck with aluminum.
I think they're just wrong.
The wrong one.
I think they're just wrong.
Americans are always wrong.
How many?
So, with the G of gas, would that just be of the reaction too? Like, it's not like a combination of both?
That would be for one specific gas. That's for one specific gas. All right, so I'm going to tell you where I'm going with this so you can have a bearing. There's nothing you need to write down. In fact, if you want to, here's an example. This is where I'm going to derive something. I'm going to try to go fast. You don't have to write it down. As I say with all derivations, I just want you to see how I got the expression. I like this reaction because two things. Number one, it's all gases. The second thing is that all the coefficients of the three terms are different. I got a 1 coefficient, 3, and a 2. We'll see why we need those. Now, as I had on the previous slide, the free energy of any gas is equal to its standard free energy. For an element, it would be 0, by the way. So for this term would be 0 for nitrogen. Plus RT times the natural log of its pressure. Now remember, in this reaction, the pressure of nitrogen will change. It's going to start at a certain value, and at the end, it's going to have a new value. So that means that the free energy of the nitrogen is going to change as well. Is it going to go up or down? We don't know yet. I think we do know. The nitrogen's pressure, what's going to happen to it? It's a reactant. Assuming the reaction goes to the right, what's going to happen to the pressure of nitrogen? What happens to the pressure of a reactant if it's a gas in a reaction? Does it go up or down? Come on, commit to something. Yeah. We start with nitrogen. We have to have some nitrogen at the beginning. What's going to happen to its pressure as the reaction happens?
Goes down.
It's going to go down. Thank you. Thank you, Dave. You knew that a long time ago, too. So yeah, the pressure that's going to go down. So if the pressure of nitrogen goes down, that means the natural log of its pressure is going to go down as well. And so this entire term is going to go down. Therefore, the free energy of the nitrogen is going to go down. Its pressure is lower at the end, so it has less energy. The free energy of the hydrogen would be the same expression. It's standard free energy plus RT times its natural log of its pressure. And then even of the product, it turns out that the free energy of the product is going to go up because its pressure is going to go up as the reaction proceeds. So the delta G of this reaction would be the free energy of the products minus the free energy of the reactants. Yes, we know how to find delta G. This is going to be a different way of finding delta G without using the table. And besides that, this is not at standard conditions. We can only use the table when we're at standard conditions. So we can actually find these values. These values are going to be constant. They're what the delta G is at standard conditions. Yeah?
What time is it? Oh, is this just like a faster way of doing it? Because we have to do it this way. And not just on the table.
No, it's going to turn out that we're going to have to use this new equation when we're not finding the standard delta G. And there's going to be a little bit more to it than that. Did you do all the problems over the weekend?
I think I have like a few left.
Did you have to do any where we had to find Q?
For what?
A problem where you had to use a Q.
Huh?
You didn't do that.
How do you?
All right, so you'll need this. Okay, as I said, I'm going to try to go fast. Is anybody going to plan to try to follow along by writing something?
No.
Yeah, that's fine. That's fine. Just see if you can keep up as I try to write frantically and get through this. Okay?
Yes, I will look very attentive.
That's what I hope for. Thank you. So the delta G of that reaction, remember what the reaction is. It was 2N2. I'll write it color-coded as before, plus 3 hydrogens. And I just did this wrong. It was just 1N2. Yields 2 NH3. I need to get rid of that first 2 right here. Oops. All right, so there's our reaction. So the delta G of this thing would be the free energy of the products minus the free energy of the reactants. Now we have an expression for free energy. It was that big ugly thing that was on the previous slide. I don't know about you. So delta G of the reaction is this. For the G of NH3, it's going to be 2 times the G naught of NH3 plus RT times the natural log of the pressure of NH3. Oh, that was nice. What a nice thing to put in instead of just calling it G of NH3. Put in that big thing. Minus, oh boy, here we go. Now we have to subtract a quantity. And I'm going to do my best to try to fit this whole quantity into that space. In green, where my N2 is, it's going to look like this. Standard G of N2 plus RT times the natural log of the pressure of N2. That had a coefficient of 1, so I didn't have a coefficient in this term. And then it's plus the 2 times, not 2, it was, I color-coded this wrong, didn't I? Ah, my gosh.
It's okay.
Okay, I'm just going to get rid of this. So we used the color coding from the previous page. 2 times the 3 hydrogens, which is, no, it was 3, not 2. Sorry. This is the last time I'll mess up.
Okay.
Ever?
No, just in the next 5 minutes.
Oh, okay.
So that would be 3 times the standard G of hydrogen plus RT ln of the pressure of hydrogen. Okay, try to squeeze that in there. And I have to close my parentheses, but there it is. Oh man, what a big mess. It's going to get a little bit more messy, then we'll start to clean it up. So what should we do here? Let's distribute our coefficients, the 2 into that quantity and the 3 into that quantity. And another step, I'm going to put my delta G terms, my G terms all together. So let's get at it again. Okay, I'll just do this. So that equals, going to distribute the 2 into these two terms. 2G naught of NH3 plus 2 RT ln of the pressure of NH3. Now I'm also going to distribute my negative sign. I got 4 terms inside of this quantity that I have to distribute the negative sign to. So if I miss one, then yell out to me. So this one doesn't have a coefficient. It's just standard of N2 free energy plus, no, I just did it. Minus RT natural log of the pressure of N2. So I'm going to distribute the negative sign from there and the 3 from there. So it's going to be minus 3 standard G of H2 minus 3 RT ln of the pressure of H2. Okay, well, there's that. It also says to combine your G terms. I got 3 G terms. 1, 2, 3. Notice how my G terms are G with a little naught sign on them. Remember what that means. That's standard free energy. Okay. So rewriting it again, I'm going to do this. Delta G equals, not A, that's delta. I'm going to write my G terms just in black now. It's going to be 2 G naught of NH3 minus G naught of N2 minus 3 G naught of H2. And what do we have? Plus, in blue, 2 RT natural log of the pressure of NH3 minus RT natural log of the pressure of N2 minus 3 RT natural log of the pressure of H2. And every time I just run out of room with my H2 down there. That red is for H2. All right, so I've done all this. You're still awake, thank you for staying awake. Now it's going to start getting good. That was all a lot of mess. But now we can start putting things together. Like this right here. What do I have in my black quantity? I have the free energy of NH3, which the product, remember what the chemical equation is. NH3 is the product, and then these other two things, the elements, are the reactant. So I have the free energy of NH3 times 2 minus the 2 reactants with their coefficients. What is that? That's just the standard delta G, the products minus the reactants. So this thing right here I can just replace with delta G naught. That's what that is. Those are the table values that we look up. And then these terms over here, it looks like they all have an RT term to them. I'm going to clean that up by just factoring out the RT, and it's going to look like this. So over here at the beginning, I have delta G of the reaction equals, now I have delta G naught. That has replaced this whole thing. That's delta G naught. That's just looking it up in the table, products minus reactants. And then the RT is going to come out and what is left inside of here. I have just 2 ln of the pressure of NH3 minus ln of the pressure of N2 minus 3 times the ln of the pressure of H2. Oh, I had room for the H2 this time. Okay, pre-calc and calc math takers, those of you that are familiar with logs, you know some of the properties of logs. When I have a coefficient in front of a log term, what would I do with that coefficient? Do what? Raise it to that power. Raise it to the power, whatever you're taking the natural log of. 2 times natural log of the pressure is the same thing as the natural log of the pressure squared. Yes? And I have a coefficient over there that I can do that with as well. So I'm going to rewrite this one more time on this page, and then we'll take it to the next page where we'll be done. I'll have my thing over there. Okay, so it's ln of pressure of NH3 squared minus ln of the pressure of N2 minus ln of the pressure of H2 cubed. Like that. This equation, if I go to the next slide, that's that equation up here. It's the same thing. I got delta G standard plus RT times this whole quantity. I have raised the coefficients on the powers, on the pressures. See that? One more thing about when you have the natural log of something minus the natural log of something else, what else can you do to simplify that? If I have, yes, divide what? Yeah, it would be ln of this term over that term, right? And in fact, I have two things being subtracted, so I'm going to have 2 in the denominator. You with me? Okay, so that is where I'm going to end. It's going to be delta G of the reaction equals delta G standard plus RT times the natural log of the pressure of NH3 squared over the pressure of N2 times the pressure of H2 cubed.
What's delta V naught?
That's the standard delta G that you use the book and do just products minus reactants. Yep. So this one is a constant. You have to know that this is a constant value. This does not change. Remember, I was talking to you about how the delta G of the reaction is constantly changing because the natural log of the pressures of everything is changing. This is constantly changing, but this is not. This is a constant value.
It's not.
It's not changing.
Wait, so is this the final one?
Not quite.
Oh, okay.
But here's why it's not quite. This is the chemical equation we were working with. It was nitrogen plus 3 hydrogens yields 2 NH3. Now I'm going to challenge your brain, your memory really. There was something that we did last year at Chem 1 at the end of the year.
I sort of tuned out.
I understand. Somebody will remember this though. Where we had to take the pressure of the products over the pressure. It was like the ratio of the products to reactants. That's what this is. Because NH3 is the product, the N2 and the H2 are the reactants. They're on the bottom. And any coefficients are raised to powers.
Oh, yeah.
Where did you see
I
that?
remember this.
You do. You've seen this before.
Equilibrium.
Jazz, say it again.
Equilibrium?
That was the equilibrium constant.
Oh yeah.
When you have a reaction equilibrium, the equilibrium constant, we call it K, was found by taking last year was the concentration. Concentration of the products or the concentration of the reactants. But the pressure ratio is the same thing. Now, have I said anything about this thing being in equilibrium?
No.
I never said anything about that. We're going to give this a different name. We're going to call it Q. I know last year we called it a K, and we will eventually call it K, but not quite yet. Because right now, Q is going to be known as the reaction quotient. That's where it gets its name Q. It's the reaction quotient. This is where you're going to want to start writing something down. Because at the beginning of a reaction, now everybody stop all your daydreaming and Instagram checking and all that and listen to this. Q. At the beginning of a reaction, you don't have any products yet. You only have the reactants. It's the beginning. What would the value of Q be at the beginning of the reaction? It's products of reactants. 0. You don't have any products yet. The numerator is 0. Yes? As the reaction starts and it proceeds, the Q is going to start to increase from 0. And it's going to go up. And it will continue to go up. As long as the reaction is going this way, we're making more products. We're using up the reactants, so that comes down. And so that ratio is constantly changing as the reaction proceeds. Now, if the reaction went to completion, if the reaction goes to completion, what number does Q approach? Yeah, it becomes infinite or eventually undefined. If I run out of one of my reactants, I got 0 in the denominator. We'll say it approaches infinity. Q does. Okay? So we have to know that in a reaction, at the beginning, you don't have any products, Q is 0. as the reaction starts. Q goes up, 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 up. So Q is constantly changing in the reaction. Here is the reaction that's written in a concise way. Delta G of the reaction equals the standard delta G plus RT times the ln of Q. This term, remember, I told you is a constant. This is what you get when you take the products, moieties, reactants from the book values. The standard delta G is a constant. However, the Q is constantly changing. Therefore, this term is constantly changing. The delta G, the non-standard delta G, is constantly changing in the reaction. And therefore, if this term is negative, this term is what we're looking at because that's the actual reaction with the quantities that we're dealing with in the reaction. If this term is negative, then that means the reaction is proceeding to the right spontaneously. Yes?
So how do you find Q? You just
You have to be given what the pressure of the products and reactants are at some point in the
why
reaction.
don't we just write out the equation with like the pressure over the terms of the product?
Yeah, they have to give you the pressures of everything. They would, like in this case, they would give you the pressure of the nitrogen, the hydrogen, and the NH3. So what the implication with this sentence is this. If delta G is negative, it's going to go to the right. But it doesn't necessarily mean it's going to go to the right all the way and run out of a reactant. It might stop before it runs out of reactants. And the entire story is written by this delta G term. Here's the next thing. If this delta G ever becomes 0, which it can, that means the reaction hits equilibrium. If that delta G is 0, it means it no longer is spontaneously going to the right. It's got to be negative to go to the right. It's not going to go to the left because it's got to be positive to go to the left. So if delta G hits 0, that means the reaction stops. And that's what we know is equilibrium.
But in the beginning, when it is 0, like remember because it's like blank over 0, right? Like
Well, this term was 0. It doesn't make the whole thing 0 because you still got that term right there. Yeah, yeah. Okay, so this brings up the concept of equilibrium. This is what equilibrium is. It's when the reaction has reached a point at which it no longer is driven one direction or the other, so it just stops. Even though there's still reactants there, they were reacting, but then they stopped. Well, how come? It's because the reaction, I think of equilibrium as the reaction has reached its point of comfort. The reaction kind of does this. It says, yes, this is good. And it just stops. It's like, okay, I'm good. I'm good right here.
I like that little demonstration.
You can relate to that, right? All right, so at that point in the reaction, we're going to rename Q. This is the point at which Q becomes K. It's only that point. It's only at equilibrium that we're going to call Q K.
You guys ever complain about the alphabet or something?
We just take advantage of the whole thing. Yeah. All right, and so that gives us just one last mathematical relationship, and that's this. When we're at equilibrium,
No, go away.
this is the last slide, so we're good. See you tomorrow.
So which one's important? The bottom one and the box?
The one that's in the box. When we're at equilibrium, that means the delta G on the left is 0. So I can just, I would replace Q with K and move it over to the 0 side. So that means that standard delta G is equal to negative RT times the ln of K.
Not that.
We'll use this a lot in this class. Not only in this chapter, but in other chapters as well. This is a, because this relates the delta G term to what the K value is. Mathematically, if K is a positive number, or a number bigger than 1, that means delta G is going to be negative. And that means something to us when delta G is negative. If K is less than 1, What do you know about the log of something that's less than 1? Yeah, it's possible. No, and I know what you mean, because if you, the answer to the log of something can't be negative.
Yeah, that's what I meant to say.
I know that's what you meant. But if you take the log of something that that is less than 1, that means that it's going to give you a negative value, and so you're going to have a negative of negative. That means that delta G is positive.
Oh, you mean like,
So the value of K, when you take the natural log, it means something in terms of the reaction. You can predict what the reaction is going to do. I had an analogy that I wanted to use for what equilibrium was. I don't have enough time. It's like a story that has to develop. Oh, I love my analogy. I'll start the hour tomorrow with it. I think you'll appreciate it. So we'll stop there. You can do a lot of the problems now. You'll be surprised at how many you can do from today's discussion. Yeah, what a treat.